Einstein used the example of a train travelling along an embankment at a velocity v, and a man walking along inside the train with a velocity w. He asks, with what velocity is the man travelling relative to the stationary embankment? He directs us to use capital W to represent this relative velocity. The answer given by the classical theorem of the addition of velocities is straightforward. Capital W equals V plus W. Einstein warned us that this answer would prove to be incorrect. We come to the problem if, instead of the man walking, we substitute a ray of light being turned on in the carriage. And then we ask Einstein's question. What is the velocity of the ray of light relative to the embankment? For with the classical theorem, we now get capital W equals V plus C, which means W, the relative speed, is greater than the speed of light. If we preserve the law of the constancy of the velocity of light in a vacuum, then this result cannot be maintained. At this point in his book, Einstein turns to the Lorentz transformation to resolve the issue. The values x, y, z, and t all refer to these two coordinate systems, where system K represents the stationary embankment and system K1 represents the train travelling at velocity v. We are now almost ready to derive from the Lorentz transformation an equation for the addition of velocities. But first, we need to make some stipulations and definitions. V is the velocity of the train relative to K1. W is the velocity of a body, a man inside the train, moving relative to the train. W, capital W, is velocity of the body moving relative to K. In general, velocity is defined as distance travelled divided by the time taken to travel that distance, or the change in the x-coordinate divided by the change in time. Velocity W is delta of distance x1 divided by delta of time t1. Therefore, W equals delta x1 over delta t1. Velocity capital W is delta of distance x divided by delta of time t. Therefore, capital W equals delta x over delta t. As we are attempting to calculate the values relative to the k coordinate system, it is convenient to use the inverse Lorentz transformation. We will adopt the convention of making gamma equal to the Lorentz factor. So the transformations can be written like this. As the first step in the derivation, we can simply write down the transformations for x and t. We are trying to calculate velocity, so as an interim step, we divide x by t. The gammas will then cancel out. But we actually need to determine the change or delta in x and the delta in t. So we replace x, x1, t and t1 with their deltas. If you are wondering why we have not applied the delta to c and v, that is because they are constants and do not change. We also now need to perform a manipulation of the equation in order to isolate the expression we are looking for. We are going to multiply both sides by 1, but we will make 1 equal to 1 over delta t1 divided by 1 over delta t1. Having carried out this operation, we arrive at this equation, with the left side remaining the same, as it has been multiplied by 1, and the right-hand side as displayed. We complete the right side and arrive at this equation. We now refer to the stipulations we made earlier. We find delta x over delta t is equal to capital W. Having established this, we look at the right side of the equation. Here we find that our earlier stipulation defined delta x1 over delta t1 to be equal to W. Performing the substitution, we arrive at this final equation, which is identical to that obtained by Einstein. He states that this equation corresponds to the theorem of addition for velocities in one direction according to the theory of relativity,